Today we're learning how to calculate equilibrium constants if we're given equilibrium concentrations or pressures. We're also learning how to find equilibrium concentrations or pressures if we're given an equilibrium constant. We're going to introduce the idea of an ice table to calculate those concentrations instead of doing mole ratios. Just to save time, I'll be using those for the next 3 chapters. So it's a pretty important or useful concept. First of all, how do you calculate equilibrium constants? So the example says we have nitrogen reacting with hydrogen and making ammonia. So at equilibrium, it gives us some concentrations. And it says calculate K. The temperature is irrelevant. The reason that problems usually say that is just to show you that, yeah, it is at equilibrium. So what we're going to do is just set up the equation. So the equilibrium constant, capital K, is equal to the products on the top raised to their coefficients over the reactants on the bottom multiplied by each other and raised to their coefficients. So then you just plug in the concentrations and we would get 37,950.7. But if we're going to use significant figures, we should probably have 2 sig figs. You can also use partial pressures to calculate equilibrium constants. If you do that, then you get the equilibrium constant calculated with partial pressures, which is abbreviated capital K sub P. You would calculate that with the partial pressures of the products over the partial pressures of the reactants raised to their coefficients. It would not necessarily be the same number. So that's why it's important to put the subscript there. There's a math equation that converts between the 2 types, but we don't need to use it. Okay, next, how do we calculate equilibrium concentrations or pressures? So the problem says, for example, if you have the reactant A is forming 2 reactant B's or product B's, and if it says you start with 1 molar A and you wind up with 0.8 molar A at equilibrium, what's the equilibrium concentration of B? So because this gives you the change in A, you can calculate it just with a mole ratio. You'd say 0.2 molar A times 2 moles of B comes from over 1 mole of A, and you would get your answer for the change in B. But I'm going to introduce right now the idea of an ice table, which is just using those coefficients in table form instead of a ratio form, and I'll save some time in the next 3 chapters. So ice table, instead of a mole ratio, we're going to put the initial, oh, I misspoke. Okay, so this is how you would do it again with a mole ratio. Just find the change in how much is used and then use your mole ratio. So kind of 2 steps, and you have to think through it, and every problem is a little bit different, whereas with the ice table, everything's going to be the same. So we could do that, or we could use the ice table. So what you do in an ice table always, so take some time on this, maybe write down the steps. You write the equation, the balanced equation, and then you write ICE at the left. That stands for initial concentrations or pressures, the change, and the amount that's left at equilibrium, so that's the answer line. And then before you do anything else, I recommend that you always put negative of any coefficient there is for the reactants because it's getting used up, so the change is negative, and leave parentheses. And then for all the products, put positive of any coefficient there is and leave parentheses for the change line. That's because if you wait to do it later, then you might forget the negative sign, or you might forget the coefficients. It's just less likely to make an error if you always do it the same way in these problems. Okay, so then we can fill in the initial conditions. So it says we have 1 molar of A, we're assuming you have 0 of B. For the change, I guess we don't have to do it that way. For the equilibrium amount, it tells us A is 0.8. And for the change then, that must mean, since the equilibrium is 0.8 and the initial is 1, that the change is 0.2. So I can just look at it. You could set it up in an algebraic equation if you want. 1 minus 1x equals 0.8, so x is 0.2. So then fill it in on both sides here. The thing in parentheses is always going to be the same since we are adjusting for the coefficient outside the parentheses. And so now we have everything we need to find the equilibrium concentration of B, just add together. So 0 plus 2 times 0.2 is 0.4. So then the second part of this problem says, what's the equilibrium constant? So we can just write the equilibrium expression from the balanced chemical equation, products to their coefficients over reactants to their coefficients. So and then you plug in the equilibrium line. So on the top we have 0.4 for B, on the bottom we have 0.8 for A, and you wind up with 0.2. I don't know if I've already told you, but equilibrium constant is defined to be unitless, just to make it easy so you don't have to worry about units, you don't have to put in units. Okay, so those problems are pretty easy because they have all the numbers, and if you need to, you can use a mole ratio. All the other problems are easy, of course, too, because they're all solved the same way with the ICE table. But when you're asked for equilibrium concentrations and not told what the change is, but given the equilibrium constant instead, sometimes solving for them is a little bit tricky. If you have an Inspire, it makes this a lot easier. So I recommend you learn how to do that. I'll show you after you try it yourself. And for the AP test, if you don't have one, try to borrow one from a friend or from the library, and that will make these problems much faster. So our example here says 2A forms C plus D. It says, what are the equilibrium concentrations if the equilibrium constant is 1.8 times 10 to the negative fifth? By the way, that's the equilibrium constant for acetic acid, and it's also the equilibrium constant for ammonia, which means that ammonia and acetic acid are the same strength of acid as ammonia is a base, and it gives you the initial concentration of A. Okay, we're not going to solve these today, just set them up. Just so we have a little bit less to learn at a time because the setup is most important. So always write the balanced equation. Next to it on the left, put I, C, and E for initial change in equilibrium. Okay, what do we do next? The change line. So we're going to put negative coefficient on reactants, positive coefficient on the products, and leave parentheses. Do that for each reactant and product. Okay, for the initial line, we know A is 1 molar because it tells us. We're going to assume the products are 0. For the change line, I've told you that these numbers in parentheses are always the same. We don't know what it is, it doesn't tell us the change, so just put in a X for all of them. And the equilibrium line, that's what we're solving for, but to set it up, you just add the initial and the change. So 1 minus 2x, x, and x. So then to set up how to solve it, you write the equilibrium expression. So K equals products over reactants raised to their coefficients. And then you plug in your equilibrium line. So you have your equilibrium constant, which is given to you, and you have your equilibrium line 1x, 1x, and 1 minus 2x. Make sure that if there's a coefficient that it affects the x, and it also affects the power, the reactant, I guess it's not a reactant order anymore, the part of the equilibrium expression. So that's all we'll do now, and so you can just solve for x with your Inspire. It'll do that for you really easily. If you don't know how, I'll show you in a future class. You can stop watching now if the starter made sense to you, the Q and the reaction quotient, where you just plug in actual concentrations and see if it's equal to K or not. If that was tricky for you, then the next part of this video will go over that, which is objectives 3, F, and G. So as promised, here's a little bit more about the reaction quotient if the starter wasn't enough. So Q is calculated, the reaction quotient is calculated just like K is, only you use actual concentrations that the problem gives you instead of equilibrium concentrations. The idea is you find out, are you at equilibrium? So in this problem, it gives you K, and it gives you moles and volumes. We're going to have to actually calculate concentrations. We can't just plug in the 3 moles because that's not the same as concentration, and so then when we square the products, for example, that's not going to be equal. So in this problem, we're going to calculate Q. It's going to be product to its coefficient raised to its coefficient over the reactants raised to their coefficients, which are just 1 and 1. And then we're going to plug in the actual concentrations. So it's going to be 3 moles divided by 1.5 liters is 2 moles per liter for everything. So that's going to give us a reaction quotient, a Q of 1. So now we just need to compare it to K and find out if it's at equilibrium. So is 1 equal to 115? No, it's not. So that means it's not at equilibrium. Our next objective is asking us, well, how will it change to reach equilibrium? So the example is the same problem again, so this is just kind of a continuation. So Q is less than K in this example. 1 is less than 1.15 tenths in the second. So that means that, I guess I'm going to go back to the previous slide. That means since Q or K, the equilibrium expression or reaction quotient expression, is calculated products over reactants. If Q is less than K, we can look at it as, oh, well, there's not enough products, not enough of the thing on the top for it to be at equilibrium. So that means that it is going to have some of the products, some of the reactants collide more and become some more products. So that's called a shift to the right, or the reaction will proceed to the right. That means it will go in the direction of the products. Reactants will get used up and turn into products. Okay, so a summary of what happens. You can figure this out yourself, but if Q is equal to K, it's at equilibrium. If Q is more than K, then that means that there are too many products to be at equilibrium, so the reaction will shift or proceed to the left to use up some products and make more reactants. And if Q is less than K, we already saw that one, it will shift to the right to reach equilibrium.